about all the numbers, all the integers between -2 and 3. That would be -2, -1, 0, 1, 2, 3. And I mean, in some ways it's similar to the set above it, because the smallest element is -2 and the largest is 3, but we can't really call that all numbers between -2 and 3 because we're skipping over all the in-betweens, all the decimals and all the fractions. So we call this a discrete set. A discrete set, you can actually count the numbers that are in it. You can list them all, right? Whereas in the continuous set, like there's an infinite number of values in there, right? But here we just have 1, 2, 3, 4, 5, 6 numbers. And so the way that we represent discrete sets, we can't use interval notation because intervals include all the decimals and fractions. So to express a discrete set, we just have to list all the values. So we use curly brackets for set notation, but unlike set builder notation, we're not listing properties of the numbers in the set, we're just listing the numbers in the set. So in this case, -2, -1, 0, 1, 2, 3. Those are the only numbers that are in the set. So like 1.5, not in there. We can combine the two. I mean, this doesn't come up super often, but there's a few graphs where we'll see it. So I might have 0, 1, 2, 3, 4. I maybe have the set from here to here. And then just that value right there. So I can't express this entire set. If we think of the entire set as what's in red, I can't express that using just an interval or just a discrete set, right? Because sort of the left side of it is an interval and the right side of it is just a single point. So we'll use both and then combine them. So on the left there we have the interval -2 to 0. And then that single point is just the number 2. So it's just the set containing the single value 2. In order to make this one set, we use this symbol, which is referred to as the union of two sets. It's saying that the set I've created is everything in that set and everything in that set put together. That union symbol, it looks like a U. It's not really a U. So if you put tails on your U's, don't put tails on your union symbols. But it's easy to remember that it's union because it looks like a U. So that's just the way that we make a single set out of two separate sets. It's not anything super crazy mathematical. It's just saying I'm putting these two things together. Okay, a couple other special cases. If I want to do the set of all real numbers, except, say, -1. So the entire number line is the set of all real numbers, and I want to exclude just one value from that. So we could use an open point here to say that -1 is not in my set. And I want all the real numbers that are less than -1. Notice that I didn't start at -2 because I want to get infinitely close to -1. I just don't actually want to be equal to -1. So like -1.000000000000001 is in there. And then the same on the right side. Everything greater. So this is really like two separate sets. It's like all numbers that are less than -1, and all numbers that are greater than -1, right? That's every single real number except for -1. So in interval notation, on our number line, we can use like our soft brackets and, well, in this case, no hard brackets, but we can use soft brackets on both sides to show that I'm not including it on either side. And so in interval notation, this is going to be the set -infinity up to -1. And then this is the set -1 up to infinity. And then just like we did in the previous example, we'll just put those together into a single set using a union. Notice the soft brackets at -1. If I put a hard bracket right here, that would include -1, and this would be the set of all real numbers, right? It would be all the way up to -1, including -1, and all the way up to infinity, right? So whenever you're just skipping over a single value, you have to have soft brackets on both intervals. And then the last one is the set of all real numbers. Which, of course, is the entire number line. And the only reason I bring it up is just there's a few different ways of writing it. So if we have the set of all real numbers in interval notation, we always go from the smallest number to the largest, right? And when there isn't a smallest number, it means we go all the way down to -infinity. So all real numbers starts at -infinity, but then it turns out there's not a largest number either. And so we have to go all the way up to +infinity. And so the set of all real numbers in interval notation is just -infinity to infinity. Another way you can write that is this symbol is the symbol for the set of all real numbers. So when we ask for domains and ranges and your answer is all real numbers, I don't care how you give it. Like, even when we specify we want answers in interval notation, we're mostly talking more like the previous example, like if it's all real numbers and you do the R, like, totally fine. Okay, so that's just like some of the ways to express or the special cases as far as sets go that are going to come up as we're finding domains and ranges of sets. So let's start with definitions. What is the domain of a function? When you guys learned this the other day, you may have learned it in terms of domain of a relation, right? But functions are just a special case of relations. You guys remember what the domain is? Yeah, it's the set of all the inputs. So if you take every single input, combine it into one set, that's the domain. So all the possible things that I can plug into the function. So it's the set of all possible inputs. When we're talking numerically, when we say possible inputs, we mean like numbers that you can actually do the operation with, right? Like if I have the function f of x equals 1 divided by x, well, x can't be 0 because I can't divide 1 by 0. And so 0 wouldn't be in the domain because that's not a valid input to the function. The function's not defined because the operation is not defined for that number. So it's all the inputs that make sense to actually put into the function that will give you an output. And then what's the range? I bet at least 50% of you know the answer to this and you're just not saying it.
All possible outputs.
Yeah, the range is all the possible outputs. So it's the set of all outputs. And what's kind of implied in that definition is that in order to be the output of a function, you have to have like an element of the domain that actually like gets you there, right? So like if we defined a function where the domain was everybody in this room, and then the function paired each of you with the dorm that you live in. Like, if none of you live in Yellowstone, then Yellowstone's not part of the range. Even though, like, we'd sort of be like, the range is all the dorms. But it's really only all your dorms, because we have to have one of you pairing to each dorm in the range. So we can't have something in the range that doesn't have something in the domain that gets us there. So all our outputs, range, all our inputs, domain. So let's start with graphs, because they're kind of the easiest way to see these. And we'll do 2 of them. Let's do that guy, and that guy looks good. So when we're looking at this graphically, the domain is just the set of all the x values on the graph of a function, and the range is the set of all y values on the graph. So x, yes?
This is probably getting a bit ahead, but sure. What would you call it on the, like a z-axis or an extra axis? Would it still be a domain or a range?
So it depends. Yes, but when you have a function that's defined in 3 dimensions, it's not like there's 3 different sets. It's like the domain could be a set of ordered pairs x, y, and then the function maps it onto a single number on the z-axis. So the domain would be like the set of ordered pairs, and then the range would be all the possible values of z. So there's still just a domain and range, because the function only pairs 2 sets.
So it would be like just having an extra input.
Right. It would just be, the inputs would just be different types of objects. They'd be like ordered pairs rather than single numbers. Or it could be the other way. The output could be the ordered pairs. So on a graph, like I said, the domain is all the x values, the range is all the y values. The hardest part about this is just keeping them separate. Like when we look at the domain, we only want to look at x values. When we look at the range, we only want to look at y values. So in this first graph, so the function is defined just by the ordered pairs where we have points. And my domain, is that going to be a discrete set or a continuous set? So can you count the number of x values? Yeah, that function is defined by just 7 ordered pairs. They're just 7 discrete points, right? I can't draw, if I start at the left side and draw to the right side, I'm covering lots of space that's not included in my function. I have to pick up my pencil to get from point to point. And so this is a discrete set, and it's just the set of all x values. And when we talk about the graph of a function, we're talking about, like, in this case, those 7 points. Like, all x values are on every graph, right, every grid. But like here we're talking about the points on that curve. Here we're talking about just those 7 points is what defines the function. And so our domain is, well, the smallest one looks like -3, and -2, -1, 0, 1, 2, 3. And that's our domain. Notice we can't just say like all the numbers from -3 to 3, because we have to skip over those decimals and fractions, right? So we're listing just the integers. So then the range is going to be all the y values. So you guys write down what you think the range is. Okay, is it going to be a discrete set or an interval? Discrete, right? So in general, to tell, you ask yourself, like, if you can count the number of y values. In this case, we can, right? There's a discrete number of them as opposed to a range of y values. So we're going to use set notation. What's the smallest number in my range? -4. Mm-hmm. And what else? Mm-hmm.
2 and 4.
Yeah, there you go. And notice that we didn't repeat ourselves. So even though there's like 2 points that have a y value of 0, we just put 0 in there once. So the set contains all the values, and then you can use them as many times as you want. You don't have to list them corresponding to the number of times they show up on the graph.
As long as it's not x, right? Because that would make it not a function.
Right, so we won't have, if it's a function, then we won't have multiple points with the same x value. But just in general, in sets, we never repeat values, even if we use them more than once. We just list them once. Okay, so let's try this guy. This guy is a continuous graph, which means I'm going to use intervals. And when we do domain and range here, you want to think of the domain as like the leftmost point up to the rightmost point. And then the range, the way we read, like we read top to bottom, and so it's tempting to think top to bottom. But remember that intervals go from the smallest value to the largest value. So when we do range, we want to go from the bottommost point to the topmost point on the graph. So my domain so if I look at the left of my graph, there's an arrow here. Anytime there is an arrow on the left of the graph, your domain goes to negative infinity. Even if it looks like it's getting really, really steep and it's getting close to vertical, because it never can actually be vertical, even if it looks vertical, because if it became a vertical line, it would no longer be a function. So even if it gets really steep, we have to assume it's going slightly to the left. It's just going really, really slowly. So eventually it'll get to negative infinity. So on the left of our graph, we're starting at negative infinity. And again, we're just looking at x values here, right? So, and then the rightmost point on the graph is right here. My curve does not go past that point on the right. And so we're going to go up to, what is it, 3. And I'm not including 3 because that point is open. And so what we're saying here is if you pick any number between negative 8 and 3, somebody pick a number between, that is not an 8. I read it sideways. Between negative infinity and 3. Somebody pick a number between negative infinity and 3. Maybe one that's on the graph, though. 1. So if I find an x value of 1, there will be a point on my graph corresponding to that x value. If I pick like negative 2.3, 1, 2, it's like right here, there's a point on my graph corresponding to that x value. So when I say the domain is negative infinity to 3, we're saying that every single number in that interval corresponds to some point on the graph. It doesn't matter what the y value of it is, but there's some point with that x value. So let's do the range. So again, since intervals go from smallest to largest, for the range, we always go from the bottom, the lowest point, to the top, the highest point. So my function does not go below that y value. And then on the top, I have an arrow pointing up. So it's going to go all the way up to infinity. So the smallest value in my range is negative 3. And then it's going to go all the way up to infinity. And that means the same thing. If I pick a number between negative 3 and infinity, and I find that on the y-axis, there's going to be at least one point on my graph that corresponds to that. So like if I pick the number, I don't know, 1.5 right here, here's a point on my graph, and here's a point on my graph that has that height. It has that y value. So we're thinking of them completely separately. Notice that like where we got like that negative infinity for the domain doesn't correspond to the same place on the graph where we got that negative 3 for the range. So we think of them completely separately. We think of left to right and bottom to top. Does that make sense? I see furrowed brows. You guys want to try one? Where are you? There we go. I don't like that one. I want it to do this. There we go. Pretend I can draw. That's a closed point. Okay, go ahead and find the domain and the range of that function. My function starts here, and then there's an arrow on the right. So I go from -7 to infinity. Now in this case, so in the last example, that point on the right was open, right? It wasn't filled in, and that's why we use soft brackets. So here, the point is filled in, so that point is actually part of our function. So we'll use a hard bracket at -7 to show that that point is included. And then for our range, we're going down. And then the very top, my graph does not go above that point. So -infinity up to 7. And again, we're going to include 7. This can be a little tricky because sometimes it's like, well, does it actually hit 7? The only time you'll use a soft bracket is if you have an open point like we had here. Otherwise, we assume that we actually make it there, because otherwise it's like, what do we do, 6.9 or 6.95? Like it's hard to tell exactly what it is. So if it looks like it goes up to 7, we just assume there is a point there at 7. Does that make sense? Yeah. Okay, so that's why we have closed brackets on either end. Any questions on this? You feel pretty good about it? Good. Okay, so let's talk finding domains algebraically. And this is sort of like the meat of the whole thing. You know, it's nice to be able to look at a graph and be like, I know what the x and y values are, but when we can find domains of functions that are defined by formulas, that has applications that you'll use throughout calculus when you get there. And so this is probably one of the most important things that we'll learn all semester. So we'll spend a bit of time on it. When we talk about finding a domain algebraically, what we're doing is talking about, like, I have a function such as f of x equals 2x plus 9. And when we ask for the domain of that function, what we're asking is what numbers does it make sense to plug in for x? So we always look at the operations that are in the rule. So the rule here is multiply your input by 2 and add 9. So the operations we've got are multiplication and addition. Now it's kind of hard when I say, like, what numbers can you multiply by 2? Like, there's a lot of choices, right? And it's sort of daunting to think you're like, I have to run through every single possible number and make sure I can multiply it by 2. I usually think of 3 different things: negative numbers, 0, and positive numbers. So can I multiply negative numbers by 2? Can I multiply 0 by 2? You get 0. Can I multiply positive numbers by 2? Yeah. So all real numbers make sense as far as the multiplication. What about adding 9? Is there anything I can't add 9 to? You can add to any number, right? So the domain of this function is all real numbers, because if I plug in any number, you can pick any real number, plug it in, and you'll get a numerical value as an output. And so we say that this function is defined for all real numbers, meaning that the domain is the set of all real numbers. So when we find domains, we most often think about restrictions. We start with the set of all real numbers, and then we say what operations are in this rule and what restrictions do those operations have. So we're going to go through a list of all the operations that we know and think about restrictions. So let's start with addition. We already decided we can add anything, right? If we have a function like f of x equals x plus 5, I can put a negative number in for x, I can put 0 in for x, I can put a positive in for x. So we say addition is defined for all real numbers, right? Remember that symbol is the set of all real numbers, which means there are no restrictions. So if I see addition in a function, that doesn't cause any restriction on the domain. We're going to be writing that statement like 100 times, so I'm going to abbreviate it with just the symbol for all real numbers, which means it's defined for all real numbers. So what about subtraction? So like addition was like a function such as f of x equals x plus 1. What if I had a function like f of x equals x minus 1? Any restrictions there? I can subtract 1 from a negative, right? And 0, and a positive. So again, no restrictions. It's defined for all real numbers. What about multiplication?
It's just repeated addition.
Right, it's just repeated addition, right? So if we can add any numbers, we can also multiply any numbers. So all real numbers. So this would be something like f of x equals 2x, right? It's just multiplication. This is getting boring, yeah. It's going to get exciting soon. So division, we have two different ways of thinking about division. We can think of division as what numbers we can divide. Oops. So the number that's in the top of the fraction. So for example, f of x equals x divided by 4. My input is being divided by the number 4 as opposed to dividing by my input. Are there any numbers that I can't divide by the number 4? So can I divide a negative by 4? Can I divide a positive by 4? Can I divide 0 by 4? Mm-hmm. So if I have, so it's the whole, if you have an iPhone, you should ask Siri what 0 divided by 0 is, because it's funny. But the whole analogy for division is like the cookies, right? So if I have 0 cookies and I have 4 friends, how many cookies does each of my friends get? 0. There is a numerical answer to that question, right? It happens to be 0, so my friends think I suck, but that is a numerical answer. So you actually get an output of 0 if you put an input of 0 into this function. So this is actually defined for all real numbers. You can divide any number by the number 4. The other way that we can think of division is numbers we can divide by. That's the bottom of a fraction. So that would be like f of x equals 4 divided by x. We're dividing by our input. Can I divide by a negative? Can I divide by a positive? Can I divide by 0? Finally, something new. We can't divide by 0, right? You can think of it in the same way. Like if I have 4 cookies and I have no friends, how many cookies does each of my friends get? Well, it's not 0 because I don't even have any friends to get 0 cookies, right? Like I've just got these 4 cookies and it doesn't even make sense to say how many cookies do I give Ryan if Ryan doesn't exist, right? So it's sort of like if I say how much money is in your wallet and your wallet is empty, you can say there's no money in it. But if I say how much money is in your wallet and you don't own a wallet, you're like, what the hell, I don't own a wallet, right? So you can't divide by 0 because the question doesn't make sense. Like the idea of dividing something among nothing, no groups, doesn't make sense. The other way to think of it is like a pizza, right? So if you have 1 piece of pizza and I give you a knife and I say divide this into 0 pieces, like every time you cut the pizza, you get more pieces. It's impossible to get 0 pieces because you have 1 and you're not allowed to eat because that's subtraction. So like, but cutting will just give you more and more. You'll never get nothing. So you cannot divide by 0. Which means that there is a domain restriction. In this case, the domain restriction would be that x cannot be 0. So we'd say that the domain is all real numbers except for 0. So all numbers less than 0 and all numbers greater than 0. Because the only thing I can't divide by is 0. So every other number is in my domain. However, that's not always the case because my domain or my denominator isn't always x. So the domain restriction is found by finding the values denominator that make the denominator 0. So for instance, if my denominator was x minus 1, then x could be anything except for 1, because if I put 1 into my denominator, it would make x minus 1 into 0. Does that make sense? So it's not that x can't be 0, it's that whatever the domain or the denominator is cannot be 0. And that's your domain restriction. And we will do lots of examples of these, so you'll get to see this in action. So next thing, exponents. Well, they're kind of boring. It's just all real numbers again. Because exponents are just repeated multiplication. So if there's no restrictions on numbers that you can multiply, then there's no restrictions on numbers that you can raise to a power. And then square roots. We're going to talk about square roots predominantly because we haven't really talked about other radicals. But in general, what we're about to say applies to all even roots. So we know like a square root undoes x squared. A 4th root undoes x to the 4th. A 6th root undoes x to the 6th. So if the exponent it undoes is even, then what we're about to say will apply to it. And it's a little different for the odds. So can I take the square root of a negative? And by the way, in case you've learned about other things, we're talking all about real valued functions in this class, so imaginary numbers are over there. So you can take the square root of a negative, you just get an imaginary number, but we're assuming that all our functions are real valued, so we only care about the real numbers. So can I take the square root of a negative? Yeah. Let's try it. So the square root of negative 4 is the number that you square to get negative 4, right? So if the square root of negative 4 was a, that would mean that a squared was equal to negative 4. But what happens if you square a negative?
You get a not real number.
No, if you square it, not the square root.
Oh, so it turns even?
Yeah, you get a positive, right? If you do a negative times a negative. And if you square a positive, you get a positive. So that can never happen. There's not any number that I can multiply by itself to get a negative number. So I can't take the square root of a negative number. Can I take the square root of 0?
0 times 0?
Yeah, 0 times 0 is 0, so the square root of 0 is 0. I just said 0. But, can I take the square root of a positive? Sure. So we can't take the square root of a negative. So the radicand, we call it, which is what is under. Does it make more sense if I say under to you or inside? Like if I'm talking about that thing right there. Is that inside the radical or under the radical? Okay, I'll say inside. I've always thought under, and it occurred to me that maybe that makes no sense. Inside the radical. So it's not the square root itself, it's just what is inside there. Can't be negative. So to find the domain, we're going to take that radicand. Well, if it can't be negative, it can be either equal to 0 or it can be greater than 0, right? Positive or 0. So greater than or equal to 0. That's going to do it for today. I have a worksheet for you, but I want to do more examples of this before I have you do that. So no worksheet over the weekend. There is a My Math Lab assignment, mostly graphs and stuff. So do the online, but ignore that written. And then